Hello fellow Scratchers, and welcome back to part 3 of our series creating a tiled scrolling platformer in Scratch. And wow, this is going to be a good one. We are going to introduce a playable character to the game and delve into the world of tile collisions. The bad news is that unlike Sprite costume collisions, we need to do a lot more scripting to pull it off. But the great news is that not only will our scripts run faster than Sprite sensing collisions, but they will also work off-screen and allow us to know what collided with what. This is crucial for making really awesome games in Scratch. So stay with me and let's get scratching. Okay, continuing from where we left off in episode 2, make sure we have the Mario sprite selected. He's not visible yet, so click the show icon here to make him visible. Yay, there he is. I'll click and drag him into a free space. This also ensures he's brought in front of all the other sprites in the game. Now, gosh, he's really small, so set his size to 200 just here. And then finally, set his direction mode to left-right. This makes him simply flip directions when he's facing left or right. That's great, Mario's in the game. But if I run the project, well, he kind of looks like he's scrolling around the level, but nah, that's just wishful thinking. He's simply sitting where we left him and doesn't know anything about scrolling levels yet. To begin with, let's get him controlled by the keyboard. Make with me a new block named Reset Player, ticking to run without screen refresh. We will put all the scripts in here that set the player's starting position and state. We need to include 2 new variables to store our player's real position on the level. Make the first one named simply X. Now let's just hold it right there for a moment. You've no idea how much I struggled with naming this variable. I wanted to call it PlayerX, but having a very specific name would not make it easy to copy scripts between sprites, so we will go with the simple name X. Good. Then we'll need to make a Y variable for this sprite only, and set them both to 100. This will be the player's start position on the level. Next, move the set camera X and Y scripts to here, replacing them with our new reset player block. Lastly, it is a good idea to use a move camera block after setting up the player to ensure the camera is not out of bounds. Next, create a new custom block named game loop. Now, because a game loop is a long-running script, we must leave the run without screen refresh unchecked. You got that? Excellent. Now, bring the forever loop down into the new define block and replace it with a call to this new block. Add a broadcast. For the new event, we'll name Move Player. The order of the broadcasts is very important. We want the player to move first, and then we'll update the camera position before finally redrawing all the tiles. This is to avoid sprites appearing to lag behind the scrolling of the level. Bring in a when I receive move player hat block. Make a new variable named SpeedX for this sprite only. This will represent Mario's current horizontal speed, that is the velocity along the x-axis, left and right. Now I want to show you a really neat trick. Bring in a set SpeedX block and set it to key right arrow pressed. Now run the project and see the value of SpeedX changing from false to true when we hold down the right arrow key. Okay, no surprises there, but look what happens when we place a minus block around the key press block. The value has changed from true-false to 1 or 0. Because Scratch knows we are working with numbers, due to the subtract operator, it has helpfully converted the true-false value to a 1-0 value. We can use this to our advantage. See, if we place a key left arrow pressed in the right-hand side of the minus operator and test again, we are able to get 1 for right, 0 for no direction, and -1 for left. And all this from one line of script. Awesome. We can simply multiply this by 6 and we have a very quick way of changing the speed. So make a new variable named SpeedY for this sprite only, and we'll do the same for the up and down keys. 6 multiplied by up key minus down key. Next, we actually move the player, introducing a change X by SpeedX, followed by a change Y by SpeedY. Bring the move camera block down from the game loop to here, we want to position the camera right after we've updated the player's position on the level. Finally, let's position the Mario sprite on the screen. Just use a regular go-to XY with our standard X minus camera X and Y minus camera Y. Great, so it's testing time. Click the green flag and use the arrow keys to move Mario. We can still use the camera X and Y scrollers to scroll the level, but don't forget to click back on the stage after doing this, otherwise the arrow keys stop working. Well, that's funky, but my hand is getting tired of operating the camera sliders. Let's get the camera to follow Mario automatically. Locate the Define Move a Camera script. Here at the top, set camera X to X. Right away we can test this and see how the camera is following the player left and right, nicely fenced in on the left and right by the edge of the level. It would be easy to do the same for the camera Y, but instead let's do something a little better. Change camera Y by Y subtracted camera Y, all divided by 4. We can test this to see how the camera now tracks more smoothly up and down. This is better for jumping games as it avoids any sharp up and down movements of the camera when the player is quickly jumping around. Try different values instead of 4 to track faster or slower, but for us 4 is a very good value. Right, we can finally hide those camera sliders from the screen. Yay! So far so good. The movement is excellent, but unless we are some kind of ghoul, we should really do something about walking through solid walls. Okay, I hope you've got your wits about you because this requires some more tricky scripting. To make it easier to follow, we'll break the process down into 4 steps. Step 1 is to calculate the location of a point on the level grid. Step 2, determining the tile under that point. Step 3, handling point collisions. And Step 4, handling larger sprite collisions. So here we go. Step 1, calculate the location of a point on the level grid. Rather than working with the Mario sprite, we'll open the costume editor and create a new costume and draw a small dot in the very centre, just here. This will be easier to work with than the Mario sprite for the next few tasks. Remember our explanation of how we use a simple number square to give a unique index to each tile in the level grid? We are going to create a custom block that, given a position, X and Y, will give us back the tile at that location. We'll make a new custom block, get tile at X, add a numeric input, X, a text label of Y, and another input of Y. Click to run without screen refresh. We'll use this block right after we update the player's Y variable in the game loop. Pass into it the X and Y of our player. Create a new variable named TileGridX for this sprite only. Now look again at this tile grid. Given the X and Y position of the player, we want to first calculate how many tiles across and up the screen the player is. Luckily, this is easy to do. We just divide the X and Y position by the tile size 32. So back in the code, set our TileGridX to the floor of the new input variable X. Divide it by 32. The floor operator is used to round numbers down to their nearest whole number. We'll create another new variable, TileGridY, and do the same thing for the Y input. Okay, run the project, and if we move the Mario dot to the bottom left tile of the level, we will see that TileGridX and Y are both 0. As I walk upwards, our TileGridY variable increases by 1 for each tile. Walking to the right has a similar effect on TileGridX, and we can use this to calculate the unique index of the tile in the grid list. Now we want the actual tile index, so create a new variable naming it TileIndex for this sprite only. Now look at our number square example again. The script for calculating the tile index from the grid X and Y is quite straightforward. The first tile starts at 1. Then we add the grid Y to get to here. Finally, we add grid X multiplied by grid height to get us to the correct tile index. So, putting that into code, add a set tile index to 1 plus grid tile Y plus grid tile x times grid height. Let's run the project again and see if this works as expected. We can check that the bottom left corner of the level is indeed tile index 1. Moving up, we'll add 1 to this number for each grid tile, and moving right should add 20, assuming our grid height is still the original 20 tiles high. That's working really well. I'll just hide these variable reporters. Okay, so step 2, determining the tile under that point. Since we already have the tile index, getting the corresponding tile costume out of the tile grid list is now super easy. Make a new variable named tile for this sprite only, and set it to item tile index of tile grid. And that's it. I told you that was going to be easy. Let's run the project again. This is really awesome. If you remember our key, tile costume 2 is the blank tile, 9 the golden tile, and 10 the wooden tile. As we pass over the tiles in the level, we see that we are now picking up the correct costume number from the grid list, just as we intended. Perfect. Okay, so step 3, handling point collisions. We now have a way to detect what tile we are touching using our getTileAt costume block. It's not a great stretch then to now be able to look for collisions and try to prevent them. We'll start by doing it the easy way. Bring in a new if tile is greater than 2. Remember tile 2 is the blank one. So this collision will be true for any non-blank tile. If this is the case, then we have collided and we change the player's y value back to where it came from, that is, negative speed y. Let's do the same for the change x, remembering to also add a getTileAt block, like this. Okay, run the project and let's have a wander around. Oh yes, this is looking good. We have been able to prevent the player dot walking through the walls. This is fun. However, if we now swap the player's sprite back to Mario and test again, we shall find that we are not quite there yet. Our clever collision detection is only looking for a single collision point in the centre of the player's sprite. It doesn't know anything about handling collisions for a sprite with a width and height. So, step 4. Handling larger sprite collisions. The left and right hand collisions are not such a problem, but the head and feet need to be addressed. We'll do this by defining the player's height, and then testing for collisions not just at the central point, but at his head and feet too. Make a new variable named height for this sprite only. Within the reset player script, set height to 24. This is actually half the full height of the sprite in case you are wondering. It's just easier to work with half sizes. To avoid repetition of scripts, create a new custom block named fix collision in direction dx : adding a numeric input dx, then a text label dy : and another numeric input dy. Ensure this is running without screen refresh. We'll use it in place of both of the getTileAt blocks here, moving one of the if conditions into the define block we just created. We only pass into the fix collision block the amount we just changed speed x or y by. And this has freed us to have both the change x and change y scripts in here together. This is a good point just to retest the scripts to ensure that they are still working as before. Good. We now have one script handling both the horizontal and vertical collisions. Now you're not going to believe me, but let's make yet one more custom block named fix collision at point x : an input of x, a label of y : and an input of y. And we'll swap this out for the getTileXY that we just moved. We'll pass in the sprite's x and y variables so that it knows where to look for collisions, and then within the define block, plug the x and y input parameters to the getTile block. So here we are checking just the central point of Mario. Let's duplicate the fixed point collision twice more, changing the top usage to check at Mario's feet by subtracting height from Y, and the bottom to check his head by adding height to Y. To keep track of whether any of these points collided, we make a new variable named solid for this sprite only, and set it to the blank value before we use the fixed point blocks. Now at the end of the define fixed point collision script, we add the if block that checks whether tile is greater than 2. If a collision has occurred, then we set solid to the number 10. Right now, this value doesn't mean much, except that any number larger than 0 is some kind of solid collision. I've chosen 10 to mean very solid. We can now update the if under the calls to fix point to confirm whether solid has been set to a value greater than 0. This indicates that one or more of the above collision checks has indeed registered a collision. We can run this to see the effect. Ah yes, this is much better. Much better indeed. Collisions at his feet work extremely well, as do the ones at his head. Good work if you've made it this far. We are not going to worry about giving Mario any defined width at present, as to be honest, he works pretty well without it. We'll revisit this later. Our next move in developing this project will be to give our player a more platforming feel. The scripts for movement will only get more complex, so let's split up the code with custom blocks for handling player keyboard input. Make with me a new block named handle keys -left right. Run without screen refresh. This block is replacing the set speed X block in our move player script. Let's update this script to give the player a little acceleration. Make a new variable named key walk for all sprites and set it to the right arrow key. Take away the left arrow key. Then we will set speed X to speed X multiplied by 0.8. This simulates friction, slowing the player down. Add to this key walk multiplied by 2. This will cause the player to accelerate in this direction. Give this a test. Oh, nice! The left and right movement feels much more natural and fluid. Next, we'll add in some gravity and jumping. Make a new block named handle keys -jump and run without screen refresh. This will replace the set speed Y block. Firstly, let's handle the jump key. Wrap the set speed Y in an if, and use the key up arrow pressed as the trigger. We'll set speed Y to 14 for a nice quick upwards thrust. Now let's handle gravity. So we'll change speed Y by -2, accelerating our player downwards. We'll place a cap on how fast he can fall using an if speed Y is less than -22. Then set speed Y to -22. This way, his downward speed will never exceed -22 pixels. Okay, time for another test. Now, this is feeling more real. Perhaps a little more Flappy Bird than Mario, but that's okay. We will improve things no end going forwards. What is important is that his collisions work well. And do they? Well, not as well as you may have hoped. Introducing variable speeds of movement has revealed an issue with how we fix a collision after it has occurred. Firstly, after a collision, we need to set the player's speed back to 0. Find the define fix collisions in direction script, and see where we resolve a collision by changing the position back by negative a dx and dy. Insert an if-else block after that and check for dx equaling 0. If this is true, then we have collided by moving up or down, so set speed y to 0. Otherwise, it was a sideways collision, so set speed x to 0. We can test this again. It should now fix some of the oddness after a collision. Yep, we do now see the player perfectly touching the floor after each jump. But it almost looks like he's bouncing back on impact. Did you see that? This is down to a second and more complex issue due to the way we move the player back out of a solid block after a collision. See how we are just moving them back by the same amount they moved in? This does ensure the player will be out of the collision, but it often results in them ending up quite far from the wall still. We instead need to find out the smallest amount to move the player back to get them free of the collision. Now, if we were using Sprite touching level sensing blocks, we would do this by moving the player a pixel at a time away from the wall until they were no longer touching it. We could do a similar thing looping the fixed collision point blocks, but for a tile-based game it's much more efficient, and dare I say fun, to use a little maths. First, make two new variables named fixDX for this sprite only, and fixDY for this sprite only. At the start of the define fix collisions in direction script, set these new variables to the input variables dx and dy. This is so that we can make use of them later. Now we'll remove the change x, change y from the script for the time being. Now scroll to the define fix point collision script. We are going to need another two variables, so make a mod x for this sprite only, and a mod y also for this sprite only. We'll set them to the side here using the x and y input variables. Set mod x to x modulus 32, and mod y to y modulus 32. Look at this diagram. Notice how this point has collided with a tile block. To push this point out of the tile, we need to know how far the point is from the next grid line. Mod to the rescue. The distance from previous grid line to the point y is calculated using y mod 32. Therefore, to move the collision point upwards out of this block, we just need to move by the remainder of the tile's height. That is, 32 subtract y mod 32. We can code this directly. After setting mod x and mod y, add an if fix dy is less than 0. This checks that the player was moving downwards. Then, here we go, change y by 32 subtract our mod y variable, just as we described. We've only coded this for one direction, but it's a great one to test. Oh yes, falling onto the ground works like a dream. I'm well pleased with how that looks. Colliding to the left is just a reflection of the down collisions, so add an if fix dx is less than 0, then change x by 32 subtract our mod x variable. Up and right are a little different. Look at this diagram. This time we've collided from the right. We are simply overlapping by the distance from the last grid line, that is x mod 32. But because we are moving to the left, we must negate this amount. That would be 0 minus x mod 32. However, it just turns out that because we always round our numbers down when we're working with tiles, moving by this much would not take us fully out of the collision. To do so, we must subtract a tiny little bit more. Minus 0.01 should do. So, drag in an if fix dy is greater than 0. And then change y by minus 0.01, subtract mod y. This will move us down by mod y and a small amount extra. Lastly, add an if fix dx is greater than 0. Then change x by minus 0.01, subtract mod x. And with that, we are seriously done. Launch the project again with the green flag and confirm that all the collisions are working just the way we intended. And yes, they are. Amazing job. The great thing about tile games is that although the initial complexity can be a little off-putting, once you have the engine in place, things get very exciting very quickly. I'm really excited to complete the basic platforming scripts and add some player animation, and then see where we go from there. What would you like to see next? Perhaps off-screen enemies, the level designer, or should we go deeper and add drop-through and sloping platforms? Why not drop me a comment under the video? With this Scratch engine, the world is seriously our oyster. If you've enjoyed this tutorial, then please smash the like button. Don't forget to subscribe to the channel to avoid missing any next exciting videos. Until then, Scratch on, guys.